Hi everyone, welcome. My name is Brecht van Lommel. Today I'll be talking about optimizations that we worked on for the Cycles GPU renderer. There is also a second part to this talk in which Patrick Morse will talk about the integration of Cycles into USD, Hydra, and Omniverse. During this presentation, we'll be answering questions in the Q&A chat box, so feel free to ask. So what is Cycles exactly? Cycles is a path tracing renderer that's integrated in Blender. It is open source, just like Blender, free to use for everyone. It has an Apache 2 license, which means it can not only be integrated in Blender, but also in other applications. Broadly speaking, our ambitious goal is to create a modern production renderer that's free to use for everyone. Cycles supports both rendering on the CPU as well as on the GPU, and the latter is what I'll be talking about mostly today. So I initially started developing Cycles about 12 years ago now, I think. This was on NVIDIA 8800 GT on a Mac laptop with CUDA 1.1, I believe. This, of course, had a lot of limitations compared to current GPUs. And we've also added tons of features over time. We've made tons of architectural changes, but a lot of cruft and legacy had accumulated, and so it was high time to do an architectural refresh. For that reason, we started a project called Cycles X last year. The goal was to overhaul the render architecture, especially for the GPU. I worked on this together with Sergey Sharaban at the Blender Institute, and the basic idea was to create a new microkernel architecture. For some GPUs, we were using still a megakernel. For other, we had also microkernels, but not quite the same as we do now. CPU rendering was again a bit different, and all of this wasn't really ideal in terms of performance and maintenance. And so the goal of the new microkernel architecture was to improve GPU occupancy and performance over the old megakernel, to reduce compilation times, which can be quite high if you put everything in a single kernel, and also to remove code duplication between different devices and to reduce the maintenance cost over time, so that we can more easily add more features and optimizations in the future. Cycles runs on many devices. One of them obviously is the CPU. We also support rendering on NVIDIA GPUs through CUDA and optics. We support rendering on AMD GPUs through HIP, and since recently also on Apple computers through Metal. This has been an ongoing collaboration with developers from NVIDIA, AMD, Intel, and Apple for the Cycles X project, which has been really great. It has helped us port Cycles X to all these platforms and optimize it, and developers from those companies are actively contributing to the Cycles code, which is just really helpful for us. In order to be able to render on all these different devices with these different APIs, we have an abstraction layer that will handle things like memory allocation, queuing kernels, executing kernels, native ray tracing APIs, and so on. And then on the other side, we also have a shared C++ kernel code, which can be compiled for all these different APIs with different compilers. And there's a bunch of macros and templates and so on to smooth over all the differences, to be able to write mostly device-independent rendering algorithms. Now let's look at the rendering kernels. So what we do is path tracing with next event estimation, and here we see a graph where every box is one kernel. And we start from the camera. We initialize a path from a camera array, and then we find the intersection with the closest surface. If we hit something, we shade the surface. If we don't, we shade the background. When we're shading a surface, we do both direct and indirect lighting. For direct lighting, a shadow path might be generated. I'll go into more detail about that later. For indirect lighting, we trace another ray and we loop back to the intersect closest kernel. And so we keep following this graph until the path terminates. As you can see, there's different types of kernels. There's an initialization kernel, an intersection kernel, and a shading kernel type. That was the graph for a single path, but on the GPU, for efficiency, we need to render many paths at the same time, and we render a few million paths at once. And we have one big array for all the main paths and another big array for all the shadow paths. Each path state is either inactive or it has a specific kernel assigned to be executed next. And there's basically a state machine that determines which kernel executes after which one. And all these path states, they contain all the information about location of a current path, what surface it's on, or the next ray to be traced, and so on. All this data is stored in structures of array storage for efficient memory access. We also have to ensure that this doesn't take up too much memory. If you have a few million paths, it really adds up really quickly. So we do various optimizations to find the smallest data type, to leave out some data if a certain feature is not enabled or used. And overall, that really helps to reduce memory usage. This is how the basic kernel scheduling works. So we are given a number of pixels to render, a number of samples, and we first start by marking all the paths as inactive, and as long as there's any pixel samples to render, we do the following. We first check if there's enough paths active. If there's not, we find the indices of all the inactive paths in the array, and we gather those indices in an array, and we execute the init from camera kernel to initialize all those paths. Then we do a greedy scheduling algorithm where we find the kernel that the most active paths need to execute next. We gather an array of indices to all those paths, and then we execute that in one big batch. We keep repeating this loop until all the pixel samples have been rendered and all the paths have been terminated. So one consequence is that we keep all the path states at a fixed location in the path state array. But that also means that as paths get terminated, you'll get gaps in the array and it'll become fragmented. And this leads to less coherent memory access, it leads to more divergent execution, so that's not ideal for performance. In order to solve that, we regularly compact the states so that all the active paths are at the start of the array and then any free space is a big block at the end of the array. We do this at 2 points. We do it right before activating new main paths, and we do it also for the shadow path array before any kernel that can activate additional shadow paths like the shade surface kernel. There is a real cost to this type of compaction. Moving around a bunch of memory is not free, and so we also have a heuristic to only do it when there is enough fragmentation for it to be worth it. Overall, we found that this helps improve performance by a few %, and there's an additional benefit that because there's one big block of free space at the end of the array, it simplifies the GPU side implementation of activating new paths. Another part of this is that we do shader sorting. So when you execute the shade surface kernel, it does a whole bunch of stuff. It evaluates shader nodes, it evaluates BSDFs, it samples BSDFs, and for different shaders, those operations can be quite different, and it helps a lot to sort the kernel execution by shader. And so the way we do this, we don't do a full sorting algorithm, we do kind of a simple bucket sort type of thing. And the way it works is that we have a shader counter for every shader in the scene where we count the number of paths that are scheduled to execute that shader next. Then right before we schedule the shade surface kernel, we construct an array of path indices that is sorted by shader. And the way we do this is we construct a prefix sum over the shader counter, which enables us to really quickly make an array of sorted indices. We also experimented with more complex sorting algorithms, more conditions, but we didn't really have any success with that so far. And with this simple shader sorting, we found that it already helps a lot, especially in the more complex scenes where you have tons of objects and tons of shaders. It really improves coherence. On the simpler scenes, it doesn't help so much, but it also has very little overhead. So it's really worth enabling. For direct lighting, we need to trace shadow rays. And for this, we create shadow paths that are fully independent from the main path. Initially, we had them more tightly coupled, but we found that duplicating a bit of state so that the shadow path can be accumulated separately in an array while the main path continues, it really helps improve coherence. You can get a big batch of shadow paths to be executed at once, and the little extra memory usage was worth it to be able to do this more flexible scheduling. The reason we talk about a full shadow path is that we're not just tracing one single shadow ray. We also need to take into account transparency, both from surfaces and from volumes. So we're talking about cutout opacity, for example, for leaves on a tree. For volumes, obviously, there's always, they're rarely fully opaque, and we need to compute that. And the way we do this is that we have one intersection kernel that finds any transparent intersections and another shading kernel that does the shading evaluation. One problem here is that on the GPU, we only have limited memory, but you can find potentially a huge amount of transparent intersections along a single ray. So how do we solve this? Well, we record a fixed number of transparent intersections, the n closest from the start of the ray. Then we shade those, and then if there's potentially more transparent intersections to be found, we loop back to the intersection kernel, and we repeat this loop until we get to the end of the shadow ray. Obviously, if you find an opaque intersection, you're done immediately, and you don't need to do any shading at all. But for the cases where you do find them, there's a loop. We found this to be reasonably efficient, especially for cutout opacity, but there's a few cases where it gets pretty expensive. And one particular one was the case of transparent hair. We had a few production files where every hair has transparency, and tracing rays through curves is already pretty expensive. Having to do it multiple times is even more expensive. And our solution to that was basically to avoid executing the shading kernel at all and to avoid recording intersections at all for this case. And so what we do is we bake the transparency at the curve control points, and in the intersection kernel we immediately accumulate the opacity. And that really helps a lot. So we're considering doing this also for more cases. If you have a cutout opacity for leaves, for example, if it's just a single image texture controlling it, we could potentially evaluate that image texture as well inside the intersection kernel, and then only leave the more expensive procedural shader evaluation for a separate shader kernel. We haven't done that yet, but we think it's promising. Up to now, I've only talked about rendering surfaces, but when we add volumes and subsurface scattering to the mix, it gets a bit more complicated. So there's 3 additional nodes in the kernel graph. The first one is volume stack initialization. We need to know for a path which volumes it is inside of, and if the camera is potentially inside the volume, we need to initialize the volume stack. Then the other kernel is the shade volume kernel, where if we, after tracing an array, if we're inside a volume, then we first do the volume shading before we shade either the surface or the background. And so that volume shading kernel can do direct lighting. It can initialize a shadow path. It can also potentially scatter, in which case it immediately loops back to the intersect closest kernel, or if it doesn't scatter, it just continues forward, and then we shade the surface or the background immediately afterwards. For subsurface scattering, we also have a special kernel. With subsurface scattering, especially if you do path trace subsurface scattering, you're tracing potentially dozens of rays. And in order to make that efficient, we don't want to schedule dozens of kernels every time. So we have a single intersect subsurface kernel, which traces all the rays in a single kernel. And that integrates with the shade surface kernel. It kind of bypasses the whole indirect light loop and just does everything in a single kernel. Specifically, Cycle supports diffusion and random walk-based subsurface scattering. Both require tracing a bunch of rays in the intersect subsurface kernel, and we do that all at once. In terms of the shading, so when we hit a surface with subsurface scattering, we first compute direct lighting at that point. Typically, this would be for a specular that's layered over the subsurface scattering. Then if we sample the subsurface scattering, for indirect light, we go into the intersect subsurface kernel, and there we find the entry point. And then if we do, we run the shade surface kernel again at the entry point, and then do direct and indirect lighting for the subsurface scattering there. And from there, we can go back into the main path loop for indirect light. Another feature we support is the case where you have some real footage and you want to composite some CG objects into it. For this, we use a classic algorithm called differential rendering, and it's pretty simple. So what we want to be able to do is generate a path that gives us the shadows and indirect light that can be composited over the footage so that the CG objects integrate well into it. And for this, the user marks every object in the scene to be either a synthetic or a real object. If it's a synthetic object, we'll just render it as usual. If it's a real object, we want to have just the shadows and the indirect light that the synthetic objects add. And the basic algorithm is to trace two paths, one in a scene without the synthetic objects and one in a scene with them. And then if you compute those two into different renders, you can compute the difference or the ratio between them, and that then gives you the shadows and the indirect light that is added by the synthetic objects. And in terms of the way we implemented this in the kernel is that when you hit a real object, that is a shadow matte, we split the path into two. One that's going to trace with the synthetic objects and one without. And this is fairly efficient because we can use ray masks to trace rays with varying visibility pretty efficiently. A few details about the optics implementation. So previously we had one big mega kernel that was compiled with optics, but now that we have all these separate kernels, we can compile just the intersection kernels with optics, and all the other kernels are pure CUDA and can be pre-compiled. This really helped reduce optics runtime compilation. In many scenes, it's now less than a second, whereas previously it took quite a while. There's still a case where runtime compilation is slower, which is when you have shaders that do ray tracing for ambient occlusion or bevel. And for that, you still need to compile a bigger kernel with optics. However, it's still a lot faster than it was before. Up to now, I've talked about the kernel implementations. However, we also made changes to the render scheduling at a higher level. One thing that we're changing is that we switched from a more tile-oriented approach to a more progressive rendering approach over the whole image. The main reason for this is that we want to add more rendering algorithms like path guiding or anything learning-based, which work better if you work over the whole image. If you do it tile by tile, it's not particularly efficient. And so in order to make this type of progressive rendering more efficient, we also made a number of changes. So one thing we do is, we first start by showing one sample at a time for the first few samples, but then as we get further, we do less frequent updates and we batch together a whole bunch of samples, which improves coherence on the GPU. One thing that we found compared to tile rendering, one problem is that if you have a few pixels that are a lot more expensive to render than others, for example, hair with lots of shadow paths and transparency, especially before the optimizations that we did, then those can hold up the entire image and you're just waiting for a few paths to finish and have very low occupancy. And so for that specific case, we actually try to detect it and we check if there's low occupancy, and if so, then we increase the number of samples in each batch even more to try to keep the GPU occupied. For interactive rendering, we also have some heuristics to try to hit a certain target frames per second and adaptively adjust the resolution to that. In the interactive context, there's also a balance to be found between path tracing and denoising. We want to have interactive denoising. However, it can be pretty expensive and we don't want to spend half the time denoising and then only the other half path tracing. So we have some heuristic to balance it so you're not spending too much time denoising but still having frequent enough updates. There's also a bunch of other optimizations we did. For example, in order to display the image, we need to transfer it to an image texture, for example, in OpenGL, and we do this asynchronously now so that that kind of copy doesn't block execution of the GPU rendering kernels or the host application. So in order to be able to render very high resolution renders with rendered passes, you still really need tiling. So we do still support that. In that case, we will cache each tile to disk after it's done rendering. And then only at the very end, we load everything back and do denoising and any other post-processing afterwards, which keeps memory during rendering low. Cycles supports rendering on multiple devices at once, both CPU plus GPU as well as multiple GPUs. In this new architecture, the performance isn't ideal yet. It's not scaling as well as it did before in some cases. The big challenge is that for interactive and progressive rendering, it's really hard to predict how fast each GPU is. If all the GPUs are the same, it's easy, but it's if they're different GPUs or you have a CPU and a GPU, the relative performance depends on the scene, it depends on the number of samples that you're rendering. And so it's really hard to make an initial guess. Currently what we do is we just split the image evenly into parts and then dynamically adjust the size of those parts based on the performance of the previous setting, but that's not ideal. We're currently looking into optimizations where we split the image into smaller alternating scan lines, for example, and then distribute those, which at least gives a better initial distribution. We also want to add better initial estimates of the performance of each device and then maybe do some tweaks to the rebalancing algorithm to make it more efficient. So that's one area where there's more work to be done. Okay, so the result of this whole thing was released in Blender 3.0. You can now download it for free and try it out. Compared to the previous mega kernel implementation on NVIDIA, we have about a 2 to 7 times speed up. The speed up is bigger in the more complex scenes where you really benefit from more coherence, from shader sorting and all those kinds of optimizations. For the simpler scenes, there's a smaller speed up. Then there's also some specific features like subsurface scattering, which are much faster than the old implementation. And besides this sort of raw speed up, all the heuristics we did on the render scheduling also help improve the perceived speed up for viewport interactivity, even if the render kernels aren't necessarily faster or only a small amount faster. And so I'll show a quick demonstration of the change in viewport rendering performance. Left is before, right is after, and as you can see, the new performance is just much better. It converges much quicker, and there's less flickering when you navigate. It sort of stays more stable based on heuristics that we have. Now that the new architecture is in place, we can add improved rendering algorithms, add more production features, and that's what we're actively working on now. So because Cycles is an open source project, you can check out the source code, you can contribute patches, you can fix bugs, and everyone's welcome to get involved. Here's the link if you want to find information about how to get involved and where the source code is. I also want to take this moment to thank all the contributors that have improved Cycles a lot over the years, both companies and individuals. So with that, I'll hand things over to Patrick.
Hey everyone, my name is Patrick Moors and I'm a Senior Developer Technology Engineer at NVIDIA. Now that Brecht has gone into detail on how the Cycles renderer has advanced with this re-architecture dubbed Cycles X, I'd like to take a step back again and reiterate one of the goals of Cycles. It being a modern production renderer for everyone. But that opens the question as to how to make it usable to everyone in a way that assumes little effort. The Cycles code base is mostly standalone and as such can be integrated with other applications beside Blender, but doing so would require a fair bit of integration work. Fortunately, there is a solution, and you may have guessed the answer already based on the slide title. When Pixar open sourced USD in 2016, this included a feature called Hydra, a high-performance preview renderer. That has since evolved to a powerful framework that can deliver scene data to any renderer, while providing a common interface for applications to interact with. Hydra is seeing an increasing adoption across the industry, so connecting Cycles would immediately make it available in a wide range of applications. To that end, I'll walk through our effort of making this reality and building a Hydra Render Delegate for Cycles. I'll start with a few words on how the project came to be and on previous work in the area. Then we'll quickly go over the basics of how Hydra works and how a render delegate for Cycles fits into it. Followed by a technical deep dive into the actual implementation to explain what the code does. Spoiler, it is open source, so you can look at and dissect it yourself. I hope this serves as an example of how a Hydra Render Delegate can be implemented for an existing renderer. Finally, I'll show a demo of how all of it can be used to render with cycles from within NVIDIA Omniverse. Now, this may not be the first time you hear about the Cycles Hydra Render Delegate. Indeed, parts of this would be familiar if you saw the talk with Tension Animation at last year's GTC. It was there that the Blackbird renderer was presented, a Cycles fork including a fully featured Hydra Render Delegate. It is open source too and had a lot of amazing work go into, so it is currently supporting most of Cycles feature set with custom USD schemas. However, there are some caveats. With Blackbird being a fork of Cycles, there is inherent difficulty in keeping it up to date with upstream. Cycles X especially included a major rework of the API that has many breaking changes. In addition, the future of Blackbird is a bit uncertain. It would be beneficial to instead have a Hydra Render Delegate be part of mainline Cycles to ensure it always keeps up with its development. That's why we rewrote it from the ground up against Cycles X, while also integrating the code into the Blender repository to make it possible to continue developing it in step with the rest of Cycles. But more on that later. First, let's do a quick recap on what I'm talking about when I'm using terms like USD, Hydra, or Render Delegates. I'm guessing you're familiar with these, but USD is an acronym for Universal Scene Description, Pixar's software platform for, well, 3D scene description and exchange. It is based on the concept of plugins, which makes it very flexible and extensible. Hydra, as previously mentioned, is a framework that communicates between different scene graphs and renderers. It defines a common interface that renderers can expose and talk to by way of a render delegate. This means that with a render delegate in place for Cycles, it wouldn't be limited to being used inside Blender. It could process and render scenes from within any application that has a Hydra viewport, whether that is Omniverse Kit, USD View, or even Blender itself again via AMD's USD Hydra add-on for Blender. Hydra is essentially comprised of three components: scene delegates, render delegates, and the render index. The central piece is the render index, which is a flat representation of the scene. It is managing the correspondence between a scene and resources used inside the renderer. Feeding into the render index, we have scene delegates, which abstract the scene representation. Since the USD platform and Hydra are written with extensibility in mind, this is not a fixed component. One for USD called USD Imaging is already included as part of the platform, but could implement a scene delegate for any scene graph. Pixar did so for their Presto animation software, for example. On the other side, we have render delegates, which similarly abstract the concept of rendering. It's extensible too, so this can be anything from a rasterizer to a full-blown production path tracer like Cycles. Finally, to control all of this, an application like Blender or Omniverse Kit can provide a Hydra viewport to show the rendered images coming back, but one could also just have a standalone tool to kick off a final render through Hydra. For Cycles to fit into all this, all we need to do is implement the render delegate interface and translate it into something Cycles understands. To do this, Hydra provides a set of classes that can be overwritten to add custom logic. It all starts with Hydra calling into our plugin to create an HD Render Delegate instance. This class provides basic functionality to create other resources, primitives, set render settings, or gather statistics from the renderer. This is also the point where we can initialize the cycle session. To keep track of that session and pass it through the various other stages, Hydra conveniently provides the HD Render param class to store it in. From then on out, Hydra will call into the HD Render Delegate instance whenever the render index has deemed that a new primitive needs to be created, for example, after a new object was added to the scene. To ensure we only end up with primitives that Cycles can understand, the HD Render Delegate class provides a method to return a list of supported primitive types. Roughly speaking, Hydra differentiates between three different categories there: R-prims, which refer to render primitives, S-prims for state primitives, and B-prims for buffer primitives. R-prims exist for anything that is a renderable object placed in the scene, be that geometry or otherwise. In case of Cycles, we can simply map those to instances of its corresponding classes, as shown on the slide. Since Cycles supports meshes, curves, point clouds, and volumes, the R-prim classes of those are implemented and translate incoming attributes etc. from Hydra and set them on the associated Cycles object. S-prims contain general state that affects rendering, but they are not really renderable objects by themselves. This can be the camera, materials that apply to R-prims, lights, and so on. And finally, there are B-prims, which Hydra uses, for example, to create output buffers to store the rendered images in. For the most part, that is all there is. Implement these classes and Hydra can start talking to your renderer. Let's look at some of the implementation details with cycles. An important part of Hydra is that it is multi-threaded, meaning primitives can be created and updated on multiple threads simultaneously. Fortunately, this is not a problem with cycles, since it is multi-threading ready. Cycles performs rendering tasks on a separate thread it maintains, and therefore already supports updating the scene independently. The render thread is simply picking up those changes as soon as it is convenient for it. That means we don't have to interrupt rendering whenever Hydra calls into the Cycles Render Delegate to change a primitive. Rather, we can simply modify the corresponding object and it will be picked up soon after. There is danger on messing up the data structures when multiple threads access them simultaneously though, so there still must be a lock placed around these updates. In the code, you will see heavy use of a utility class called SceneLock, which takes care of locking the scene vertex during this. It should be noted that Hydra is using a pool design for updates, and only pulls data from the scene delegate when needed. For this purpose, it keeps track of modifications to primitives and notifies all render delegates when something changed, but it's then up to the render delegate to decide what changes it is interested in, and pull the necessary data to update its own resources. To do this, the rprim and sprim classes contain a method called sync that can be overridden. In the Cycles Render Delegate, it is implemented as shown on the right. The overall structure is very similar in all the various supported rprim and sprim types. First, the aforementioned lock is entered to ensure there is no data corruption when multiple threads try to access the scene. Secondly, we can check which parts of the primitive were changed, as passed in by Hydra via bit field of dirty bits. For those parts that did change, we then must pull the new data from the scene delegate, convert it into a representation understood by cycles, and update the associated cycles object. Meanwhile, cycles also keeps track of whether an object was modified. It does so by checking if a value differs from the existing one whenever one of the set methods is called, like the setTFM method for changing the transform in this case. So finally, after going through all possible Hydra dirty bits, can just check if that is the case and the object was indeed modified. If so, we must notify the overall cycle scene that it was updated by calling tag update, thus informing the render thread to pick up the changes. As you can see, synchronizing cycles objects like meshes and lights is pretty straightforward. It really is mainly about managing to convert all the incoming attributes and primitives like light intensity or mesh vertices to equivalent values in cycles. But what about materials? Here things become interesting, since every renderer generally handles shading differently. To be able to support this, Hydra does make little assumptions about them. It provides the ability for render delegates to declare what kinds of materials they support, called render contexts. This can be a custom format or something like materialX or MDL. We simply need to override the getMaterialRenderContext method of the HGRenderDelegate class. Hydra will then only create and notify render delegates about the materials they support, provided the scene contains them. Cycles uses its own shading system, abbreviated SVM, which consists of a graph of various shader nodes computing the shading result, including BCF nodes, math nodes, and so on. Conveniently, Hydra already supports processing node graphs for materials, so we can just store these shader nodes in USD, identified by render context token unique to cycles. Then just need to convert that graph back to a cycles shader graph in the render delegate. This means we can have Blender export out the full cycles shader graph to USD, and when rendering this USD scene in another application with the Cycles Hydra Render Delegate, we'll get the same results as if rendered natively in Blender Cycles. And for the case that a scene does not contain the exportable Cycles shader graph, USD falls back to universal render context. This is typically using nodes defined by the USD Preview Service schema. Hydra picks that up as well, so in that case can create a material cycle shader nodes that mimics the behavior of USD Preview Service. With the scene created and updated, it is time to actually perform rendering. Hydra uses the concept of render passes to describe a render iteration over the scene, like a separate render pass for shadow map generation and a main one. This is primarily useful for rasterization, whereas for a path tracer like cycles, it is conceptually sufficient to just have a single render pass doing everything. Hydra calls an overridable method called execute on the HGRenderPass class every frame, with information about what camera to render with and what arbitrary output variables, short AOVs, like color, depth, and any custom data to output. If those differ from last frame, you need to update the cycle session accordingly. To handle output, Cycles has an output driver class that can be derived from and implemented, which has methods that will be called whenever Cycles updates or finishes rendering. In the current implementation, the results are simply copied into the render buffer primitives created via Hydra. This works great to support multiple AOVs, but in case of using Cycles to render with CUDA or optics, there is a little bit of overhead associated with copying the results from the GPU to the CPU. In an application providing a Hydra viewport that displays it with OpenGL, this seems unnecessary, since it would need to copy the output back to the GPU for display again. But Cycles has a solution here too, through a separate class called DisplayDriver. It provides methods to bind an OpenGL pixel buffer object that Cycles can render into directly via interop. The Hydra Render Delegate can then create and associate an OpenGL texture with a render buffer primitive which the application can query. We can then copy the data from the pixel buffer object into that, allowing the application to make use of the GPU texture directly and avoiding the round trip through the CPU. A rough outline of the code for the RenderPass implementation is shown on the right. It first attempts to enter the log surrounding all scene updates. If it is unable to do so because another thread is currently modifying the scene, then the rest of the method is simply skipped for the time being. This way, Cycles continues to render the previous state until scene updates have completed. Otherwise, can query the requested AOV bindings from the RenderPass state that Hydra passes in and reconfigure Cycles accordingly if they changed. As a third step, the camera is queried, and all its settings are applied to the global scene camera Cycles uses for rendering. Once everything was updated, can check the Cycles scene to see if the session needs to be reset. This is where, among other things, the tech update calls seen in the primitive implementation earlier come into play. They did set the bit Cycles used to check modifications, which are checked here through the need reset method. The cycle session generally needs to be reset whenever changes to the scene happen that require path tracing to restart from scratch, for example because an object was moved or the AOV bindings changed. With all that complete, the code then ensures the render thread is running and starts it if that is not yet the case. Finally, to notify Cycles that a frame should be displayed because OpenGL interop is used, you need to call the draw method on the session every frame. This is the point where Cycles will copy current output into an OpenGL texture if requested. I've covered the important bits to get scene description into the render delegate and execute rendering now, but there's more to rendering than just scene. Cycles also has global settings one can set, like whether to render using the CPU, CUDA or optics, or whether to use denoising or not, or how many samples to render when not doing interactive rendering. Hydra has a generic interface to apply such settings via a setRenderSetting method in the HGRenderDelegate class. This accepts a token string and value and is then up to the render delegate to interpret these. Hydra also keeps track of whether render settings change this way and stores a monotonically increasing render settings version. That means rather than modifying the cycle session on every setRenderSetting call, we can instead check if this version is greater than the last frame in the RenderPass execute method and apply all render settings again in one go, right before the session may be reset anyway. But enough talk about code. Let's see it in action. Starting with Omniverse Kit version 103, it supports using Hydra Render Delegates in the viewport. You can see I have the well-known car demo scene from Blender loaded here into Kit, and I'm rendering it with Cycles. This was simply exported to USD from Blender, including the Cycles shader graph, and now renders with full fidelity inside Omniverse. And now I can use all the functionality Kit provides for modifying the scene, including simply moving the car around while never leaving USD. Similarly, I could compose new scenes here or add new objects or lights, and everything would be rendered with Cycles. It just works without re-importing things into Blender to see how it looks. In the beginning, I already spoiled that the Cycles Hydra Render Delegate is open source. In fact, you can find the patch that adds it to the Blender repository on developer.blender.org right now. Searching with the keyword Hydra will get you to it. One thing to note is that for Hydra Render Delegates, it is generally necessary to build against the exact USD version and dependencies as the application it should be used with. And that most likely differs from the one used in Blender. This means you will need to provide the right USD build by setting the CMake variables shown on the slide. For more details and review, I encourage you to check out the patch itself. And with that, I'd like to thank you for listening and staying throughout all the dry implementation details. I hope this was useful if you're considering building a Hydra Render Delegate or just interested in using cycles outside Blender. Feel free to shoot us any questions concerning both Cycles X or the Cycles Hydra Render Delegate in the Q&A following next.